identify the fault is on the load. Am I making sense?
I was thinking, like, I kind of would understand how to determine like what type of symmetrical fault it is. But for a symmetrical fault, you would see like all the voltages and all the currents have the same magnitude. But I'm trying to think of how you determine if that was a fault.
Okay, good. Good question. So it's a balance system. If it is normally it is we talk about the systems are balanced until the fault hits the system. So whether it is a symmetrical fault or unsymmetrical fault, we are talking about a balanced system. So if it is a symmetrical fault, you will see the current going to an enormously high value, and all the three sequences, positive, negative, zero sequence, will reflect the same value of current. Even if you don't know whether it is a, we don't know, right? When the fault hits, we don't know whether it's a symmetrical fault or unsymmetrical fault. Then go work on the sequence networks and see zero, positive, negative sequence. All the three are showing the same value of high current and voltage and the angle. Then you can decide it's a symmetrical fault. If it's an unsymmetrical fault, then it will show only the positive sequence or negative sequence or zero sequence. Suppose if it is a single line to ground fault, then you will see the current value is same as the zero sequence or ground current value will be the same as the positive sequence current. So positive and zero sequence will have the same current value. And if it is a negative, positive and negative are together, then you can see that positive and negative together means it's a line to line. If it involves ground, then you will see that value is reflected in the ground. Just by looking at the sequence components, we cannot say whether it's a line to line or line to ground or anything. After you learn the sequence components, after you know how to put the sequence components, then you have to connect the sequence components in a different way. I told you how to connect them. Like single line to ground fault means all the impedances are connected in series. If it's a line to line ground fault, then all the impedance must be connected in parallel. So now we are determining the impedances. After you determine the impedances, you have to connect it in the fashion that I showed in the last class. So based on that fashion, then only you are identifying which fashion is giving you the highest current. Then you can identify that current, that kind of fault has existed in the system.
So like say you find that one voltage is zero, and then the other two phases have zero current, and it's like a line of ground. Does it like tend to pan out that way?
Yes. Okay. Yes. So let's go step by step. Good question. Let's go step by step. Let's find out the impedances for each and every component. There is a different way to draw the components for each and every equipment. So let's do it, and then we will put them together in a simple power system, and then draw the equivalent circuit and identify the fault. Okay. So this is how we are doing the equivalent circuit sequence components for impedance loads or induction type of loads. Okay. Right. Next is a transmission line. So how do you draw the sequence components for transmission lines? Transmission lines is the simplest thing in the whole system. You just draw the same type of impedance for all the three components. Just reflect the same impedance. What is the transmission line impedance? Take it and put it in a zero sequence, positive sequence, negative sequence. That's it. Okay.
So for zero sequence, because usually it says that like the inductance is like 2 to 3.5 times the positive negative, just because the path for ground is farther away from the original phases.
Yes.
Does that factor in?
That is correct. That's what I put it in the last line here. Zero sequence is usually 3 times more than the positive and negative. So when you are replacing it with zero sequence, every time zero sequence, 3 times the normal value.
Okay, that's just the rule.
That is the thumb rule. Okay. 3 times the normal value. Okay. So you are taking here zero sequence, positive sequence. This is a line, okay, transmission line. positive sequence, negative sequence, zero sequence. Zero sequence must be 3 times the positive normal Z value. Okay, simple. Next is a generator. So generators and the loads more or less behave the same value, same way, but the loads are inductive nature. Generators are capacitive nature, synchronous generators. Okay, so we are having the three phase. So the difference between the loads and the generators are generators will have the voltage source, whereas the loads will not have voltage source. So look at the diagram here. Look at here. So this is representing the load. So there is no voltage source connected in any of the phases. None of the phase will have the voltage source. Whereas the same structure, when it is represented with some voltage sources, then that's a generator. So without the sources, it's just a load. Okay. With sources, it's a generator. So you're going to follow the same procedure, but you're going to include the voltage source in the sequence diagram. Okay. So because the structure is the same, the load and the generator will behave in the same way, except that the generator will have a voltage source in the sequence network. Right. So you can see here the positive sequence is connected with the voltage source, whereas the negative sequence and the zero sequence are similar to the load. Okay. Positive sequence is connected, I mean the voltage source, even though the voltage source is here in all the three phases, when you are drawing it in sequence components, only the positive sequence must have that voltage because it's a balanced network. All the three phases are carrying the same voltage value. So that voltage must be represented only in the positive sequence. Whereas negative sequence, it must be maintained as 0. Maintained 0 means you are keeping the voltage source 0. So when the voltage will become 0 in a short circuit. So you are short circuiting that terminal here in the negative sequence, and in the zero sequence you are representing it with the zero sequence components impedance, which is 3 times higher than the normal sequence. Okay, so am I making it sense? Any questions? Clear?
Is it always like this?
Always like this. This is
Or
a
it's
thumb
only
rule.
for the generator?
I mean, for the generator,
It's like
always like this. Whatever I'm saying here now is a thumb rule. Load, this is the rule. Transmission line, this is how you have to draw it. If it is a synchronous generator or generator, balanced generator, this is how you have to draw it. Just take it. Okay, it's a tablet version. Right. The complex part comes only when you are looking at the transformer, because transformer is having two non-connected things, primary and secondary, which are mutually coupled. They are not connected. They are mutually coupled. So all that mutual, so there is an impedance in the primary, there is an impedance in the secondary, there is a mutual impedance between them. So all these things need to be included in the sequence components. And there are different types of combinations can happen. Transformers can be connected in star, it can be connected in delta. If it is a star connection, then there is a ground connected. If it's a delta connection, there is no ground. So transformer is a complex part. Okay, so let's look at how to connect the transformers. What are the thumb rules for transformers and different types? Okay, so before we go into that, let's do one analysis. We know how to draw the sequence components for the load. Now let's connect it with the source. Okay, so we are not looking at the transmission line here. Ignore the transmission line. Just look at the source and the load. Now we are putting two systems together, a simplest system, and let's try to draw the sequence components for this. Okay, both are similar. It's a delta load, a delta source, delta load and a Y source. So the rules are similar, except that for the generator, positive sequence should contain the voltage source. Okay, so let's do that. Right. So you have the sequence networks. It's a neutral is grounded. So this is neutral grounded through the impedance of Zn equal to 10, and line impedance is also given. So We are just taking a generator load with the line impedance. Okay. Right. So whatever we have seen so far, we are going to put them together now. There is no transformer. Transformer is left out. Okay. So line impedance is like this, and then draw the sequence networks. So first for the source. So here this circuit is showing this part is source. Okay. This part is the line. This part is the load. Okay. Positive sequence. Let's start from the positive sequence. For the source, how do you draw the source for the positive sequence? It should include the voltage source. Okay. And in the impedance, whatever given the impedance. Okay. It is connected in Y. So the impedance can be transferred as it is. If it is delta, then only the impedance should be divided by 3. Okay. So, but the source here is Y connected. So we are just taking the impedances as it is. Okay. Generator sequence impedances are 1 is 15, negative sequence is 3, and 0 sequence is 1. Okay. So let's put it here. So starting from positive sequence, you take the generator 15 with the voltage source. And for the negative sequence, just put the impedance alone. And for the 0 sequence, put the impedance and multiply the Zn by 3. So draw positive sequence, negative sequence, 0 sequence for the generator. Okay. So just draw that thing alone. And then between the two, so what is the thing which is connecting? Generator is drawn now. So the line is connecting the generator with the load. So you have to include the line impedance. So the line impedance, what is the rule for line impedance? It's same for all the three. Okay. So the 0 sequence, positive sequence, negative sequence. And then for the load, look at the load. Load is connected in delta. So if it is connected in delta, then it should be divided by 3. Impedance must be divided by 3. Positive sequence, bring the impedance, divide by 3. Negative sequence, bring the impedance, divide by 3. Whereas 0 sequence, there is no ground connection. So leave that, put the impedance, divide by 3, leave it open. Okay. So this is how you are connecting the generator line with the load. Now you can solve the network. When you solve this network, you can say here which current can be solved here. Positive sequence current can be solved because it contains the voltage source. So you can solve it as all the three impedances are connected in series. V divided by impedance can give you the current. So you get I1. Whereas negative sequence, there is no current because there is no voltage source. Whereas here, there is no current because there is no voltage source. So I2, I3 will be 0, whereas you get only the positive sequence current. So if you see only the positive sequence current, I2, I3 are 0, then it is good. That is how it should behave. A balanced network without any fault, this is how it should look like. Is it clear how to put them together? Okay, so this answers your first question. If it is a balanced network with no fault, then you will see I1 some value, I2, I3 0. If the fault hits the system, then you will see this I1 rising to a very high level, and then you will see some values happening here in I2, I3 because the system is going to be connected in a different way. If it is a single line to ground fault, you have to take all the impedances, 0 sequence, positive sequence, negative sequence, put them in series and connect and calculate the current. When these impedances are coming in series with this one, then this one also carry the current. If it is a line to ground fault, then they will be connected in parallel. So they will also carry some current, but that current will be different from this current. Positive sequence will carry the maximum current, whereas these two current will be the same. Right.
But just curious, also, because I remember reading usually for the negative sequence, it often the current often sees like a subtransient reactance for like synchronous generators. I was wondering for like usually whenever I see synchronous generator example problems, they always show like positive sequence impedance being higher than the negative, even though like I know the positive just depends on what type of fault analysis you're trying to do, whether it's a transient, or steady state. And I always find it interesting that they always have a higher impedance for positive than the negative for and then that asynchronous generator again. C is like the highest. Or I guess that would be the lowest. I have it backwards in my mind.
You are having it in the backwards.
Yeah, no, that makes sense. Okay.
So positive sequence is the one it is giving you the subtransient,
Yeah.
and then transient, and then the steady state.
Okay, so it just takes like the combined.
Yes.
Oh, that makes sense. Okay.
All right. So moving on to the next one. So if it's a Y connect, yeah, go ahead.
What was that question? Sorry, I was just
Yeah.
wanted to hear the explanation again.
Mm-hmm. Oh, okay. So Tom's question is the impedances. I mean, we talked about the current, right? Current is going to go in 3 different phases. One is a subtransient current, another is a transient current, another is a normal current. Generators, we used to put XD, double prime, XD prime, and XD. So subtransient phase of the current is usually the current that we look at in the positive sequence. Transient side of the current is usually the current which is coming in the negative sequence and the zero sequence, and it slowly reduces. So here, though we see the networks as 3 different networks, how we can look at the current putting them together is when you are analyzing the entire fault analysis, you have to put the impedances, connect all the 3 impedances, positive sequence, negative sequence, zero sequence impedances, either in series. All of them can go in series if it's a line to ground fault. If it's a line to line fault, then only positive and negative sequence goes in series, whereas zero sequence stands alone. If it's a line to ground fault, then all the impedances are going in parallel. So all of them are coming in connection. They are all going to be connected. So when they are connected in that manner, then how much current this impedances are going to carry, how much current this is going to carry, how much current this is going to carry. That is what we are going to put together in the current curve. So the first current is coming from positive sequence because that's the first network to which we are going to connect the other networks. So the first current is always the highest current because it is coming out from the source undivided. And then negative and zero sequence are connected either in series with the positive or in parallel with the positive. So we are going to carry lesser current or the same current. So if it is connected in parallel, then the lesser current. So the peak of the negative sequence components will be lesser than the positive peak. So that's the positive peak is called the highest peak, subtransient. The negative peak is called the transient, and then the zero sequence. Making sense?
Yes, thank you.
Alfred, you got some question.
My question was, I didn't see this lecture notes on chemistry.
Oh,
Is this week 10?
this is week 10, yeah. Okay, I will double check. And repost it. Thank you. All right. So the next example is if the Y connected source applied to the balance line. Okay, so here we are looking at VAG, VBG, VCG. Calculate the source current IA, IB, IC. Right. So here, this is a continuation of the previous problem. The same problem we took, we just draw the impedance networks. Now we are applying the voltage value to that. Just apply the voltage value and try to calculate the current. This can explain much in detail about what we are talking about the currents. Okay. So substitute the values for the current. V0, V1, V2. So that you can calculate I0, I1, I2. So in this example, V0, we have to expand it in the way that we explained earlier. When we are talking about symmetrical components, we know how to expand V0, V2, V1, V2, right? So expand it in the way with the angles, okay? So P0, V1, V2, you get the, this is the voltages, okay? So these are the voltages from the phase value. So we are actually, the phase voltages are given. Now from this, you have to convert it into sequence voltages. Then only you can calculate the sequence current. Calculate the sequence current, convert it into phase current. Okay. So first step is phase voltage into sequence voltage. So phase voltage into sequence voltage, apply the formula that we talked last class. You get V0, V1, V2. And then I0, I1, I2. How do you get I0, I1, I2? Apply it to this diagram. So in this diagram, I0 supposed to be 0 because there is no voltage involved in this network. I2 supposed to be 0 because there is no voltage involved in this network. Whereas I1 will exist because this is replaced by V1. So put the V1 voltage here and solve the network, calculate the current. So that's what you are looking at here. So your I0 is 0. I1 you get this value. Whereas V1, I2 actually, even though you get so here I2 is a network. We don't put the voltage here. Voltage source here, but
Are these the same? This is 8.5, you're going over 8.6. Are they the same?
it is the same problem. Continuation of the same problem. So I2, we have the voltage V2 here. Okay. So just use the voltage and the impedance, calculate I2. Okay. So you can see here V0, I1, I2, because the voltage is here. You don't put that voltage in the network, but this is a equivalent, negative equivalent voltage. So use that voltage to calculate the I2 value. And then from I0, I1, I2, calculate IA, IB, IC. So here you can see all the three are carrying the same magnitude, almost the same magnitude. Angles are different. That shows it's a different phase because there is no fault hitting the system. Okay, if the fault hits the system, then you will see different values here and the angles are different. That can tell you what fault here. Is it making sense? Right. So this is how we are putting it here. V0, just put the voltage, whatever we calculated. V1, V2, solve the network and get the values. Okay. Right. So the next thing is the last component of the power system, transformer, which is a little bit complicated. There is a rule how these equivalent circuits are derived. Look for the detailed derivation in the textbook. But I'm just bringing you in a tablet form so that you can just remember what is required. Okay, as a rule, as a thumb rule. Okay, right. Now, zero sequence impedance is equal to the leakage impedance. So we are talking about the primary impedance, secondary impedance, and the leakage impedance. Okay, so the zero sequence impedance is equal to the leakage impedance. That's one of the thumb rule. Zero sequence equal to Z1 and Z2. Okay, right. Now, moving on here. There's a lot of rules about the positive and negative sequences. You can read it. I will take it to the diagram.
It's just a zero sequence when things get.
Yes. Yeah, it is. The zero sequence things are a little bit different for delta and Y connections because the ground connection is not existing in delta, whereas it's existing Y connection because we are talking about three-phase transformers, not single phase. Okay, right. So let's start from star. Primary is connected in star, secondary is also connected in star, with both neutrals are grounded. Okay, there are many different combinations. Primary is star, secondary is star, both neutrals are connected in connected to the ground. So this is how the connection looks like. You can see here, this is how the connection looks like. So this is the symbol that indicates what type of connection here. So in the one line diagram, we just see this line, whereas bottom we will see this one, meaning this is Y connected to the ground, Y connected to the ground. That means primary is star, secondary star, both neutrals are connected to the ground. Okay, and so this is how the actual diagram looks like. Primary ABC, secondary A prime, B prime, C prime. So if it is like this connection, then because ground is involved, then you should include the ground between A and A prime. So we are trying to, these are actually primary and secondary are mutually connected by through leakage impedance. So we have to connect, we cannot just isolate primary and secondary, right? So we have to connect them. So connect, how do you connect? Connect by the neutral, because it's going through the neutral. Because it's connected, both are connected through neutral. So you are putting the neutral in between A and A prime. Same thing for B and B primes and C and C prime. Okay. And then the next combination is star connection with only one side is neutral, other side is not grounded. Okay. You can see here, one side is, both are star. One side is grounded, other side is not grounded. So one side from A, you put the ground, but it is not connected to secondary, because secondary is not grounded. So leave that terminal open. Making sense? Right. Now the third combination, next combination is no neutral at all. Primary, secondary, no neutral. So no ground connection comes in between. Just leave it open. Okay. Then, okay. So now we are moving on to star delta combination. Primary is connected in star, secondary is connected in delta. So there is no ground here. Okay. So primary is connected in star, secondary is connected in delta. So primary, all the three elements, all the three phases are connected together. So you have to represent it with the zero sequence, whereas there is no ground here. So delta, just leave it open. Whereas in the primary, it's grounded. Delta is grounded. So the ground should be connected to the ground. Whereas, sorry, Y is grounded. So you put the ground impedance and that should be connected to Z, connected to ground. Whereas delta, just leave it open. Right. So now here, if the ground impedance comes with in the previous cases, ground is straight connected. Look at here, ground is straight connected straight to the ground without any impedance. Suppose if the impedance comes in the ground, then that impedance must be replaced by 3ZN. Okay, so it's impedance replaced by 3ZN. Whereas it's delta, so there is no connection between them. Okay, right. If both are delta, so you put the ground impedance connected to the ground on both sides, primary side, secondary side, but both are not connected here. So the ground is not connected to the phase primary or secondary. It's just grounded. Okay. So this is all we are talking only for the zero sequence. Remember, zero sequence is the one which is difficult. Positive and negative sequence are not complicated. Okay. Right. So now let's take a synchronous generator supplying power to the synchronous motor, and the neutrals of the two generators are grounded through the impedances. Draw the sequence network for this system. Find the line-to-line voltage at the ground terminals. Assume a balanced three-phase operation. Okay. So this is what we are looking at. Synchronous generator. There is a line impedance and the synchronous load. Okay. So take a generator. These are the rules, right? For the generator. I just draw the rules for the generator. So generator, voltage should be reflected in the positive side, positive sequence, negative and zero sequence should reflect only their impedances. Right. The next thing for the load. Next is the transmission line. The transmission line, positive sequence, negative sequence, zero sequence is same. There is no problem. And then the load. So the load is also positive. Load is also the same as the generator, but without the voltage source. Okay. So put them together. So first draw the generator. Draw the generator on this side. Draw the generator on this side, and then the line impedance, and then the load impedance. Okay. So load impedance. When in the zero sequence components, you can see here, load is having 3Zn on this side, and zero sequence. So zero sequence must have 3 times the impedance, whether it's a load or it's a generator. So it must be reflected, 3Zn must be reflected on both sides for zero sequence.
This is a generator to motor load.
Yes. Whereas here, generator to the motor load. So voltage source must be included in the, generator on this side, load on this side, sorry. So generator and load. So generator should be included with the voltage source. Motor should be included with the voltage source if it is present. In this question, the motor draws 5 kW of power at 0.8 power factor. So we know the voltage on the motor side. So that's why we are representing that power in terms of the voltage in the motor, not only the impedance. Okay. Right. So motor, positive sequence, negative sequence. Take the same positive sequence, just short circuit the voltages. You get the negative sequence. So the difficulty here is only drawing the positive and zero sequence. Negative sequence is replica of the positive sequence without the voltage sources. Short circuit the voltage source, not open circuit. Okay. Short circuit the voltage sources. Right. Now you get the sequence networks. Now next step is to solve them. So solve the current. So what is IM1, VGAN, VG? Okay. So you are taking VGAN is VG, which is VM1, V line 1. And once you get this one, then you can get the IM from that motor side. And then you can get the VGAN, and then from VGAN you can get the VG. It's a line voltage. Once you get the network, the rest of the steps are mathematics. Right. The next example is fault condition. So what we have seen before is without the fault. Now let's look at the fault. Okay. So it is talking about a Y connected synchronous generator, positive sequence reactance. So here the positive, negative, zero sequence are given directly. Okay. Positive sequence, negative sequence, zero sequence for the generator is given. Generator neutral is solidly grounded, meaning there is no ground impedance. Okay. There is no ZN. With the generator operating unloaded at rated voltage, a so-called single line to ground fault occurs. So we know the type of the fault. We want to identify what is the fault current value. Okay. During this fault, line to ground voltages at the generator terminals are going to this level. So at fault condition, single line to ground fault. So this is how the fault conditions are going. These are given in the phase values, like VA with respect to ground, VB with respect to ground, and VC with respect to ground. Okay. Determine the sequence components, draw the phasor diagram, and then find out the current. Okay. So we have to start from the scratch. What is generator? How to draw the sequence components for that. And then this is a generator fault, right? So we are just restricting all our arguments only to the generator. So this is the generator. This is the generator with voltages here and Zn. Okay. So now positive sequence, negative sequence, zero sequence. This is how the actual network should look like. Now replace these Z values by their actual Z values and the voltage by the actual voltage. Okay. Right. So once you replace it with the actual value, this is how it's going to look. Okay. So let's look at the rules first and then put the values. Okay. So positive sequence, negative sequence, zero sequence. You got the generator, you draw the sequence networks, and then the type of the fault is single line to ground fault. Then we have to connect the sequence networks according to the rule which is stated for that particular fault. So single line to ground fault, connect all the sequences in series. So positive sequence, negative sequence, zero sequence, all of them must be connected in series. If it is a ground impedance is reflected, then that must be replaced by 3Z. Okay, so this is the rule. Now let's see how to apply this rule to our particular case. Right, now we get this positive sequence, negative sequence, zero sequence. How we get this one? From this diagram. Positive sequence reflected with the voltage. What is the voltage we are talking about? Positive sequence voltage. So we have to convert this A, B, C into positive, negative, and zero first. Okay. And then get the positive, negative, zero sequence values and put that value there. Okay. So put the positive sequence with the voltage source with the impedance, negative sequence, zero sequence. Now, so here, negative sequence, zero sequence is just the impedance. There is no Zn. The problem states there is no solidly grounded. There is no Zn value given. So you don't need to put 3Zn there. Okay. Just put the Zn value. And then connect everything in series. When you connect them in series, you can see that the current. After you connect them in series, trace the current. Is all the impedances carrying the same current or not? Okay. So current is coming out from this source, going through this impedance, going through this impedance, coming back to this impedance. There is no 3Z here because it's solidly grounded. Okay. So all the impedances are carrying the same current. That means I0 equal to I1 equal to I2.
So in which cases will it be 3 times Z?
If the problem says, look at here, instead of solidly grounded, if it says there is a ground impedance present and it's given with the ground impedance value, then that must be reflected in this diagram.
Okay.
That must be reflected in this diagram. This is how it will be given. So that's a ground impedance. And when you are transferring it, it should be reflected as 3Z. Here it is solidly grounded, so we are just connecting it directly without any impedance. There is no impedance. No impedance means it's short circuit. It's not open circuit. Okay. So that you should understand. No impedance means it's a short circuit. Impedance value is 0. So when the impedance value will 0, it will become 0 only in the short circuit. If it's open circuit, impedance value is very high. That is not the case now. Okay. Right. I0, I1, I2. This is a voltage. All the impedances are carrying the same current. So they all added together because they are in series. Then once you get I0, I1, I2, you can calculate IA, IBIC. And from IA, IBIC, V0, V1, V2 are given. You can calculate VA, VB, VC. Now you can see clearly only one phase is affected. Other two phases are, the amplitude is the same. Phase angle is different because they are different phases. But one phase voltage is completely gone. And you can also see the current is existing in only one phase, whereas the voltages in the other two phases are 0. So the results matches with the fault condition. Okay. If the fault condition is not given, how to identify it? Then you have to try all the 3 methods. Single line to ground method, like the one shown here, line to line, line to ground, and see which one is reflecting what condition. So if this condition exists and the other two conditions are not existing, then we can say this is a single line to ground fault. You get what I mean? This is how you have to put them together.
Because I feel like it'd be telling from setup that they're like 2 voltages are the same, they know it's like a line to line, or it lets you know. I don't know. Yeah, I know what you're saying. Yeah,
if it is involving, so if 2 lines are the same, carrying high current, and the same two lines are carrying zero voltage, then it's definitely line to line. Then how will you identify it's a line to line or line to ground is based on the angle. If the ground is involved, then the angle will not be 120 degrees.
Isn't it like a line to line ground, which have two voltages that are zero, right?
Yes.
Yeah.
Two voltages are zero and two currents will be high and their phase voltage will be different. Yes. And the angle between the phases will be different. It's not equally 120. Okay. Right. So if the same problem we are looking at as a line to line fault. Suppose if you don't know the fault and we want to check all the three conditions, how do you connect the impedances? So if it is a line to line fault, then you have to connect only the two lines, positive and zero sequence in series, positive and negative sequence in series, and leave the zero sequence. Okay, that's the rule. So let's connect the impedances according to this rule. So you leave the zero sequence, connect the positive and zero sequence in series. You have the positive sequence, negative sequence, starting point of the positive sequence to the starting point here, ending point of the negative sequence to positive sequence to the ending point of the negative sequence. So trace the current now. Look at the rule. Positive sequence and negative sequence are connected in parallel. Okay, so connect them in parallel. Now trace the current. So why I'm saying always trace the current, because it doesn't mean you're connecting them in parallel. The current should be different. It may be the same. Okay, so you're connecting the circuits in parallel, but trace the current to identify whether the positive sequence current and the negative sequence current are getting divided or they are same. They same. If you know this one, then only you can identify whether the resistances are coming in series or in parallel. Even though the two circuits are connected in parallel, doesn't mean the two resistances must be in parallel. Okay, that is what I am trying to emphasize here. So after you connect the circuits, trace the circuit. So current coming out from the source, going through the positive sequence impedance, follow the line. It's coming through this impedance, follow the line, it's getting back to the source. So current is not getting divided anywhere. So this impedance and this impedance is carrying the same current, though in the opposite direction. So I1 should be negative of I2, but the current should be the same. So what it means, the two impedances are connected in series. So you can solve it like a normal KVL circuit. Take voltage source, divide by the addition of the two impedances, you get the current. So you get what you are getting is I1. Negative of I1 is I2. Okay. So you get I1, negative of I1 is I2. So you can, when you transfer it into ABC, by sequence components, zero sequence, positive sequence, negative sequence is not going to tell you the fault. You have to transfer that sequence component into phase current and phase voltage. Then only you can identify the actual fault value and the actual fault phases. Okay, you get the current, transfer it into ABC. So once you transfer it into ABC, you can clearly see that B is negative and C is positive. So that shows it affected only B and C phases, not AB, not AC. Okay, because A is 0, which shows the perfect normal condition. And also, you are not going to stop here. Every time you analyze the fault, you also have to look at the voltage. So take the voltage values, transfer it into ABC, and look at the voltages. So voltage in B and C are negative, same value. So it is clearly BC fault, not AB fault. Okay, right. Suppose if it is a line to line, instead of line to line fault, double line to ground fault. What you have to do, connect all the three impedances in parallel. Now trace the current. Convert it into ABC components. You can see here, this is 0, B and C. You can see here B and C phase angles. They are not 120 degrees apart from each other. So if it is not so, then it involves ground. Okay. Same thing for the voltage. Okay. So these are some examples that are just showing you how to put the sequence components, connect them in series and parallel to show you how to calculate the fault current. Okay, so these are much simpler than the example that we have seen so far. Impedances are given directly, find the fault current, ABC, and then three-phase fault means we are looking at only positive sequence. We are not looking at zero and negative sequence because they are not, their current's going to be zero. There's no voltage source involved. So positive sequence, just take the positive sequence and calculate the positive sequence voltages. V0 equal to V2, 0. I0 equal to I2 equal to 0. Only positive sequence current and voltage exist. Calculate it and then convert it into phase A, phase B, phase C. Then you can calculate the IA, IB, IC and convert it into VA, VB, VC. You can see IA, IB, IC, three-phase fault. So all the three currents are equal, all the three voltages are zero, and the phases are not equally distributed. So that shows it's a three-phase fault involving the ground. Okay, three-phase fault. Now, if it is a single line to ground fault with three impedances, then take the impedances, connect them in series, and then trace the current. Once you get I0, I1, I2, get IA, IB, IC, and then get VA, VB, VC. You can identify what type of fault is. V0, V1, V2, and then calculate I0, I1 because it's equal, right? So get IA, IB, IC, and then VA, VB, VC. You can see here, IA is coming 3 times IO. So if it is a single line to ground is involved. So current should jump to 3 times. Okay. So that's why I always say when ground is involved, it's 3 times the higher current. So your impedance also must be 3 times the high value so that the ground can be protected. Okay. So 3 times the value. VA, VB, VC. You can see here I value is 3 times IA. So what is Z value? That's going to be the multiplied by 3. Okay. So you get the values. Same problem, line to line fault. So if it is line to line fault, you are connecting only a positive and negative in parallel, whereas zero sequence must be left out. So calculate I1 equal to minus I2, calculate I1, I2, I0, and then IA, IB, IC, V1, V2, V0, VA, VB, VC. You can clearly see here, VA is normal, 1 per unit, whereas VB, VC are less. Whereas IA is 0, IB, IC are higher value. This is how the diagram looks like. Okay, making sense? So this is double line to ground fault. Connect all of them in parallel, then calculate all the voltages. Okay, right. So until this, we have seen how to get the symmetrical component for each and every element of the power system network, and then how to calculate the fault, how to calculate the sequence components, how to connect them for each and every fault, and then how to identify the fault values, current and the voltage. Now we are going to put everything together in a power system network, simple network, and let's analyze each and every section independently. Okay. Do you want to take a break before that? I can see you are all tired. Huh? Not your fault. It's a timing fault. It's a lunch time, I know. So the time now 2:30. Let's meet at 2:45. Take a break.
Yeah, Professor, I think we don't have this slide on Canvas.
Yeah, Alfred told me already. I will post it after the lecture.
Okay. Okay.
Thank you. So this is a complete system. What you are seeing here is generator, transformer, transmission line, step up transformer, step down transformer, and then connected to different loads. So this is a kind of a network, how we can apply the rules and solve it and find out the fault. Okay. So the system has a line to ground fault. So that's stated in the first line. Okay. So it's a line to ground fault between B and C. Assume that all positive and negative sequence reactances are 75% of their pre-fault value. So voltages are going to 75% of the pre-fault value. Right. So this is how. Now let's look at the section. Okay, each section we are going to do a zero sequence for all the sections one time, positive sequence for all the sections one time, negative sequence for all the sections one time. So that because those are going to go in different diagrams, right? So you have to find out zero sequence for everything and put them in one diagram. Positive sequence and negative sequence, they are going to go in the different diagram. Okay, so let's do that. So first thing, zero sequence. Okay. All right. Let's start here. So this is the yellow one is a positive sequence. Orange one is a negative sequence. Gray one is a zero sequence. Okay. Now this is a generator, Y connected generator. So Y connected generator. So you have to put it solidly grounded. So there is no ground connected here. Okay. So positive sequence comes with the source. Negative sequence comes with only impedance. Zero sequence comes with the impedance, but the Zn must be represented here, but later we can short circuit it if there is no impedance. Let's check one more time the problem. Is it coming with a assume that all positive negative sequences are 75% of the pre-fault value. Zero sequence values are the same and n values are equal to zero sequence value. So it has got a zero sequence value. It says zero sequence values are the same and n values are equal to zero sequence values. Okay. So we have to consider the zero sequence. Okay. Let's put the theoretical diagram first. Okay. So that's for the generator. Then for this line, all are represented by their impedances. Then for the transformer, primary side, it is Y. So when it is Y, then zero sequence should have, it's Y and delta. So the impedance must be connected here. And here the impedances and zero sequence. So positive and negative sequence just represented by the impedance for the transformers. Whereas in the zero sequence, Y side is having an impedance, common ground, whereas delta side, there is no common ground. So that should be left open. And then again for the impedance here. So this impedance, this is the line. Just represent it by the impedance. And then again transformer. So this side is delta. So this side also should be delta. So you cannot connect a delta with a star. So delta must be delta. So this side, positive sequence, negative sequence, just the impedance. Whereas zero sequence, this side is delta. So it should be connected by the impedance. Sorry, here. This side must be connected by the impedance, but it's a delta, no common ground. So that should be left open. Whereas the other side, it is star. So other side must be connected with the impedance. Right. Then this side, there is no line impedance given here. It's going directly to the, let's look at this part. Okay. So the fault is happening here. The star is the place where the fault is happening. So when the fault happens here, then we must represent it by the fault impedance. Fault impedance, the positive sequence, fault impedance, the negative sequence, fault impedance on the transformer. So this side is Y, this side is Y. This side is not grounded, this side is grounded. So which side is grounded? That impedance must be connected to the ground. Whereas the other side must be left open. Okay. So we are transferring this fault to this side, the transformer side. Okay. So can you understand this? This is a theoretical equivalent circuit of positive negative sequence for each and every component.
So I was curious about the last transformer because if one's not grounded,
Hmm.
the other is, that means what could it
Yeah, so there is this side is not grounded.
Oh, I see.
This side is Y grounded. So Y grounded. The load is parallel to the fault. So we will talk about that later.
So,
Okay.
sorry, are we only focusing up until the fault, right?
Yes.
We don't care about what happens with the Z5. And
You know, we are not looking at that one right now. We will look at it later. Okay. Right. So now the next section. So let's look at this side. Okay. So we can, so from the fault, from this side, this section is what we are drawing now. So from here, looking at the transformer now. So looking, I mean, here, look at here. So this is a load. We are talking about the load in this side. So this load is delta connected load. So that's why we are taking, I mean, this load is just the Z value. We are representing it by Z value in positive, negative. In zero sequence, you have to look at it delta or star. So this is a delta. So take the impedance and connect it to ground. I mean, there is no connection between this side. There is no ground here. Impedance must be grounded without connecting it to the other side. Okay. Now let's look at this side. Look at this side. So this side is a Y grounded. So Y is connected here and Y grounded. So impedance must go like this. Okay. Positive, negative. This side is impedance. Zero sequence. Y no connection. Whereas Y grounded, you must have the impedance. And then here again, so look at this line. This is just the line represented by the impedance. Okay, ZA. I mean here. These are parallel. So parallel, so you have to connect them in parallel. In the previous case, look at here. In this case, it is series. It is, I mean, here, look at this impedances. These impedances are in series. So you are connecting it in series on. Whereas the loads are in parallel to the fault. That's why you're connecting it in parallel. Okay. Same thing. Same thing here. So these two are ZA, ZB are in parallel. So connect them in parallel. Okay. Now put them together. So now put everything together and then represent it by its actual values. So now positive sequence. Here, this impedance, actually, what is that impedance coming from? This impedance is coming from here, from the Y connection. So it is not having any, it's a straight connection here. There is no ground impedance, okay? There is no ground impedance. So we are taking this, okay? So this section, we don't have this one. And Z1, we are putting 75% of the previous original value after fault. So Z1, original value is Z1, it's changed to 75% of Z1. Okay, 75% of Z1, this section. And then, I mean, we are talking about positive sequence. So positive sequence for transformer is just the impedance, okay? Whereas zero sequence is the one which is going to change. So positive sequence, negative sequence, the load, just connect them everything and then solve the network. So this is where the fault happens. So before the fault, how the circuit behaves, after the fault, how it behaves. So before the fault, you can just connect them. So this is going to go, this is going to go. So this circuit is going to go empty. This circuit is going to go empty. Okay. So only this side is going to exist. So, okay. So this is going to be connected. Because there is no impedance here, it's going to be connected in series. This is going to be connected in series, and this is going to be here. Okay. So connect it everything together. This is where the fault happens. This is where the fault happens. And then solve the network before this and solve the network after this. And then line to ground fault. Okay. So that we have to remember. So solve the zero sequence, positive sequence, negative sequence, get the impedances. Get the impedances. 0, positive, negative. Line to ground fault, all the impedances must be connected in parallel. So put all these impedances in parallel. Now get the values. I0, I1, I2. Change it to IA, IB, IC, and then VA, VB, VC. Okay, get IA, IB, IC, and then you can see here line to line fault. Okay, you can see B and C are at fault. Current is existing there, and they said all especially B and C. In the problem it says especially B and C, and it is reflecting here in B and C, and our calculation is correct. And you can see the voltage. Okay, so you can also calculate the voltage and see how it works. Okay, so this is one of the exercise shown in the book, and it's worked out here. So this is having a transformer. It's a generator, 2 generator. Little bit close, similar to the problem that you are working in Power World. Except that the Power World is having so many buses, but this is less buses. It's having 2 generators, 2 transformers, and there is a bus which is connecting one side and the other side. Whereas there are few more buses in between these two. This is much simpler than the Power World problem. Okay. Right. So Power World is having 7 buses. It's having only 3 buses. But the generator transformer arrangements are very similar. Okay. So the details are given also similar to your Power World problem. Okay. So this is a simpler version of how to solve your bigger Power World problem, project problem. Okay. So generator values are given, transformer values are given, transmission line values are given. Now let's see how to solve this. Take step by step. Okay. Take the transformer first. That's the complicated part. Take the transformer. Look at the transformers. Transformers are, what it says is a transformer Y to Y on this side, delta to Y on this side, solidly grounded. Okay. So let's take this transformer first, find out the equivalent. Right. Star connection with both neutrals grounded. It's very simple form. Only 0 sequence you have to look at, because that is where the difference comes. Positive and negative sequence, you are just going to transfer the impedance as it is. 0 sequence goes through different formulas. Okay, just 0 sequence, Y and Y grounded. Very simple. Just take the sequence impedance. Right. The next one is, so take the impedance here. Whereas the transformers, the positive sequence, look at here, the generator values, just take the impedances. Okay. This is Y solidly grounded. Solidly grounded means this ground impedance must be reflected in 0 sequence. Otherwise, it's just the impedance. Okay. So then the lines, the rest of the things are lines. So lines are just going to be replaced by their respective impedances. There is no load given here, so you don't need to worry about the load. Okay. Right. So positive sequence, negative sequence. So transformer, so balance 3-phase fault. It's talking about balance 3-phase fault. So we need to consider only the positive sequence. So positive sequence, the generator, positive sequence, the voltage must be reflected in the positive sequence. Okay, so this is the voltage, transformer, and the line. Okay, impedances, just their impedances. Okay, and then solve the network, you get Z1, Z2, Z3. So get Z1, Z2, Z3, and then put it in the voltage. We are looking at only positive sequence. Why? Because it's a 3-phase fault. Okay, so put it in the fault and then calculate the load current, fault current. It's just I1, I2, I3 are same. Okay, so take that one.
So in the last slide, where you converted it, you convert the impedances from delta to Y.
Because this structure here looks like a delta. So to solve the network, we need it to be in the Y connection, so that you can parallel the array. I mean, I always told you, like, trace the current. Current is coming from this source. This is one generator. Current is coming from this source. This is another generator. So these two are in series. These two are in series. But passing through here, This is the current is coming. This current is coming I2. This is I1. So all these three are in series. All these three are in series, but this is coming in parallel with these two branches. So that is what we are doing here. Series, and the series combination is coming in parallel and solve it. Okay, just solve for that current. This is how bigger network you are reducing it. Okay, so I showed you a complete network. I showed you one similar to the power wall problem. Okay, this is how we are doing the calculations. Okay, so this is a summary of what we have seen today. Hopefully, I think my battery is dying. So what I will do is I will close this one. Okay, this is still working. Right. So any questions here? Am I making it clear? Good. So now we are left with few more minutes to look at the power world problem, how to work on the homework 4. Okay. So because my battery is dying in the laptop, I will run the video that I posted already in Canvas. See, you might have seen the videos. You asked me?
You need a charger?
Yeah. Do you have
Is it like USB-C?
USB-Cs? Thank you so much. Yeah, that's enough. Okay, so let me take this here. Okay, am I sharing the screen?
I don't think so.
No.
No.
Okay.
Yeah, no, you don't.
How about now?
Yeah,
Am
I can
I?
see.
Yeah.
Okay, great. Okay, so just watch this video. I posted this video already in Canvas. Watch this video, and then let's watch this video together, and then I can explain. I can clarify your doubts if you have tried homework 4 already. If you haven't tried, then this is a self-explanation video. Okay, and I will address your problem. You said, I mean, you can share your screen and I can tell you what's your problem, what's the curve you got for this, and then we can talk about that. Okay. Wait, I think I should share the sound.
What was it of this?
Hmm?
Was it of this system? That, oh no, this is the video.
This is the video.
That was like a 2-bus system. I did it.
Mhm. Share sound. checking that is share the sound. Okay, so here I'm going to voice over my voice itself. Sorry. So when you do this run mode add-on PV curve, what we are, I mean, on the left hand side, you can see uh, the the steps to, I mean, the left hand side is the one where you are going to plot the curve. These are the prompts to plot the curve. So to plot the curve, you need to specify which bus, I mean, you cannot plot the PV curve for the entire diagram. You need to be very specific about this bus or that bus or this equipment or that equipment. For that, if you are taking a bus, mostly it is PV curve can be drawn only for the buses. Whatever the equipments connected to the buses are going to contribute to the voltage and the power and the angle and everything for that bus. Okay, right. So you need to specify one particular bus and look at what is happening in that bus. Now, if you take a bus can be connected with a generator, a transmission line, transformer, or the load. So, meaning there must be some incoming voltage or power to the bus, and there must be some outgoing voltage or the power from the bus. So, the bus is a thing which receives something and send out something. So, we have to specify what is the incoming source, what is the outgoing thing. It can be a load or it can be just the transmission line. Incoming can be from a generator or it can be from another bus. Okay, so that is what the main thing. Where from where which, I mean, if the bus is supplied by two sources, two generators, or one generator or one another one is coming from the another transmission line, then you have to specify which direction you are looking at. Are you looking at the generator side of the bus or you are looking at the transmission side of the bus? So these are the things that we are going to specify if you want to look at the power curve, power and the voltage curve. Okay, so that is the first step. What is the source? From where the source is coming? From where the input to the bus is coming? From where the output from the bus is going? That is what we are referring here as the source and the sink in this diagram. So first we have to represent the source as the incoming. Incoming can be anything. It can be from a generator or it can be from another bus. Okay. So that is what it shows. Okay. Look at this. So first you have to select source and the load, and then after that it's easy. As I said earlier, it is not necessary it should be generator. Okay, it can be anything coming inside, whatever supplying power to the load. You can just name it as incoming source, or because in this diagram it is a generator. Yeah, I'm just naming it as generator. Okay, before going to the quantity, let me explain what this things are looking like. Okay, so first thing we are looking here is the injection group. So in the injection group, we just selected what are the sources, what are the loads, and everything. Next thing is we can also select interface megawatt flow. So when you select interface megawatt flow, that is when you are selecting the incoming power from another buses or incoming power from the another transmission line. When you say injection group, you should specifically mention generator and the load. Okay, right. Then next thing here is a critical scenarios. So here we are going to, I mean, there is a section that we can implement contingencies. So we are not going to do contingencies in this course, but we will continue this power world in next term and work on the contingencies. Okay, that's going to be our first lesson in power protection. So contingencies are like situations where you, I mean, as the name suggests, it's a contingency scenario where you will have a very limited sources and very exhausting loads, and where the something which needs more power. Okay, so how are you going to work on that scenario with the limited sources? Okay, so contingency scenarios, we can say how many contingency scenarios you want to run, one or two or three or four. Okay, so that you can select here, and then you can input the contingency cases here. I will explain the contingency scenario one more time next term, first lecture. Okay, but I'm just giving you introduction to what it means. Okay, so these are the common points. So these are all like kind of a mathematic thing, like how many steps it should run, like we did the Gauss-Seidel method, how many iterations we need to do. So those kind of limitations we are doing here, we are just specifying here how many steps we need to do, what is the maximum steps, what is the convergence. You can change this, you can play with this and see how the results works. Okay, And on this side, quantities to track, it can show you what are the things that you want to track. You want to track the capacitor, you want to track the buses, you want to track any of the loads, generators, you can choose whatever you want. And then you can go here to plot the curves. Okay. Here, once it reaches the maximum point, meaning reached nodes means it's iteration. So the iterations are complete and the results are very similar between the previous iteration and the current iteration. It will say base case cannot be solved after that point. Okay, it doesn't mean like a complete base case is not solved. So if sometimes if any error comes and the base case cannot be solved in the beginning itself, then the system will not run here. Okay.
Because when I ran the test simulations, it never solved or resolved. It just like continued to try to solve it. So I think that's why my graphs came out funny. Like that never concluded.
Okay, so if that is not concluded, then you have to go back and set the limits. We will check your result.
Okay, yeah, like you said earlier, I'll share my screen.
Yeah, we will talk about that. Right, so this is what I want to show you, and you can give a try and work on homework 4. It's pretty easy. Just need a little focus, and you have. I posted the document from the Power World company. The document also in support of this video. If you want to refer, you can refer that. Okay, and then submit homework 4. Try. I would definitely ask you to give a try on this because it's not big calculation or anything, so it will give you some interesting results. Okay, so try this and submit this homework. Now, let me stop share the screen and look at. Now, creating too many screens. Stop share. Okay. So, are you, Tom? Are you here? Okay.
I'll email you the link of this recording.
Thank you.
I'll just set it up.
Here it's only one generator. Yeah. No, I think. Wait. No, close this one.
It didn't delete it. Like it just.
Yeah, go there.
For some
Yeah.
reason, it keeps trying to
Hmm.
give me like a default G1 denomination for the name. I'm like, that's
Hmm.
not the way.
There's only one load, right?
See, like it just keeps trying to this thing.
That's okay. We can select it when we are going back to the main
Oh,
screen.
because I don't even have that.
Hmm.
Oh, I see what's going on. Oh, I think I see what I did on here. Let's. So I think I need to have a participation point declared for load before I add it to
Yes.
my injection group, so that makes sense.
So we selected participation is 100% already. So when you have both, then
That's
hmm.
all the things. Okay.
Wait. Your go back to that screen. Buses. You got your KV and the load. Okay, fine. So you got your generator, nominal KV and KV. Where is the power?
Right? Yeah, like that doesn't populate. Like that's an unselectable field in terms of being able to populate yes or no. But technically, like we choose a bus to project the PV graph, so I'm just gonna choose bus two at the load power output.
Oh, that's the reason. Okay.
Right?
I think that's the reason your curve, one of the curve is going flat.
Exactly, because like, and also see I'm running this, it just like never resolves.
So select the other bus and see what happens.
Right? Cool, because I can't choose bus one for the. I guess it's under the
Yeah.
fields, maybe one load, so I guess it makes sense that it would have a load represent for the generator. But
Okay.
yeah, because like again, this just runs forever. So it's like okay, I'm just gonna go on with my life and I'll just try and plot something. So I buy, let's say, bus two PV, and then that's selected. That's selected.
You should select bus B. Yes.
And then it has those kind of like static values at the top.
Wait, can you uncheck one of the graphs to see what happens to the other graph? Oh yeah, it is moving.
Okay.
It is a constant one. Yeah.
Yeah, that's weird because like I remember, I think I got the same graphs in terms of like both the values are displayed. Like, but yeah, I did.
Because it is just one source and one load, so it's going to be constant. In my case, there are so many buses involved, so that's why it was ramping up and down. So it is okay.
For sure. And like my initial question or concern was like, how it's supposed to look? But I guess in this case, yes. In which case, then it's good.
Yeah, it's good. Okay, so I'm done for today. Next week we will start with the presentation and then I will start with the course summary first and then presentation and then the lab. Okay, that's going to be our last lab, a last lecture for this term. And today, don't forget to take the quiz too. I will open it up. Open it at 5 o'clock. Leave it open until 11:30 p.m. Okay.
Doctor, could you extend it to midnight? Because I do work tonight until 10, and I don't always get off right on time.
Okay. So I can keep it open until 1 o'clock.
Okay.
Tomorrow, I can keep it open until tomorrow morning, 9 o'clock. Is that okay?
I'll still try to get it done tonight, but if you want to do that, that also works.
Okay, I will do it until
Okay.
9.
All right. Thank you.
Okay, so we will see next week. And I'll see a few of you tomorrow. And you all have a wonderful evening. I'll see you tomorrow next week.
Yeah, I have a question.
Go ahead, Daniel.
Will the Q's cover week 10 fourth?
Huh?
I'm asking if week 10 is part of the Q's too.
I'm not getting, your voice is breaking. Anybody can understand?
Is lecture 10 a part of quiz 2?
Oh no, good question. Quiz 2 doesn't include what we discussed today until last week.
Okay.